Okay, let's dive a little bit deeper into the concept of unbiasedness. And in order to illustrate what that means, it is best to walk through an example, which you see here to the left. And specifically, I want to show why it is that when we calculate the variance, that we use the formula n-1. And the answer is we divide by n-1 because that gives us an unbiased estimator. So an unbiased estimator is one that if you were able to take from a population all possible samples, then the average of all sample values or sample statistics will be equal to the population parameter. So there are at least two unbiased estimators that you already know. One is the mean, and the other one that I will introduce to you now is the sample standard deviation when we divide by n-1. So, but let's illustrate what that means. So let's walk through that example here, and I'll quickly copy that and paste it here into Excel. So the first thing I want to show you is that the mean is an unbiased estimator. So let's calculate the mean. So the formula for the mean in Excel is average. So let's calculate the average for the population. So we assume we have a population with 4 observations, and the population mean is 10. So now I'm taking all possible samples of size 3 from the population of 4. So that means I can take 4 samples of size 3, and essentially in each sample I drop 1 from the population. So in sample 1 I drop the 4th observation, in sample 3 I drop the 3rd, in sample 2 the 2nd, and in sample 1 the 1. So here sample 1 to sample 4 are all possible samples of size 3 that you can take from a population of 4. So now let's calculate the average for each sample. So sample 1 has an average of 8. Sample 2 has an average of 9. Sample 3 has an average of 10, so that's equal to the population parameter of 10. And sample 4 has an average of 13. So now what makes the mean an unbiased estimator? So if I take the mean of all sample stats, so then we take the average of all possible sample statistics, and now you see that is equal to the mean, to the true population mean. So that 10 is the same as this 10. Okay, so now let's do the same thing using the population variance. So we want to know, is the variance an unbiased estimator? So we calculate the population variance, which is the formula divide by n. So we take all the squared deviations from the mean, divide by n. So in Excel the formula is var.p. The p stands for population. So the population variance using the formula divide by n is 31.5. So now let's do that. For sample 1, get 26. Sample 2, 38. Sample 3, 42. And sample 4, 6. So now, is the average of all possible sample statistics, or of all sample statistics from all possible samples, equal to the population parameter? Let's check. We take the average of those 4 sample statistics, and we see they're obviously not the same. So now let's do the same thing using the sample variance formula, which is dividing by n-1, and in Excel the formula is var.s, so the S stands for the sample. So now we get 42 for the population. Now let's do the same thing for the 4 samples. Sample 1, 39. Sample 2, 57. Sample 3, 63. And sample 4, 9. So now you see we always use the formula var.s. And now, does this give us an unbiased estimator? Let's double check by taking the mean of all 4 sample statistics. And you see that gives us also 42. So, in other words, using the formula dividing by n-1, that gives us an unbiased estimator in the sense that the mean of all possible sample of a sample statistic of all possible means, that average is the same than the population parameter when we use n-1. And because we know that, we get the best indicator from a sample about things that go on in the population. So it is our best estimator from a sample in order to make inferences about things that go on in the population. So unbiasedness is a crucial precondition for making sound, credible inferences from a sample about things in the population. And so now we know the mean is an unbiased estimator, and the sample variance using the formula n-1, that is an unbiased estimator. But the standard deviation, for example, would not be an unbiased estimator, because when I take the square root, that is a nonlinear transformation that will mess up things. So the best thing we can get is a formula for an unbiased estimate of the variance, and that is n-1. I leave it up to you to see that when we enter here the formula for the standard deviation, that this will not give us an unbiased estimator. Actually, I can do it quickly. Standard deviation. So now we would use the formula STDEFS. So now for the population, that is 6.48. Let's remove some of the decimals here. And 6.24. 7.55. 7.94. 3. And exactly 3. So now let's calculate the average. And now we see that is not the same. So the best thing we can do is we can make unbiased inferences from the variance. So that's the best we can do. So now we know the mean is an unbiased estimator, and the sample variance is an unbiased estimator. The population variance or the sample standard deviations are not. Okay, so one more word. If you have a large sample, actually we still will use later when we do inferential statistics, we still can use the standard deviation as a proxy for the population standard deviation. Even though it is not technically an unbiased estimator, but the greater the sample size is, the more the sample standard deviation will be equal to the population standard deviation. Anyhow, so let's just conclude here. So we know for sure that the mean is an unbiased estimator and the sample variance gives us an unbiased estimator, meaning that this is the best estimator from a sample that we can use in order to make inferences about the population. Okay, so let's just stop here, and in the next video let's continue with some more statistics of dispersion.